Ladies and gentlemen, dear colleagues, welcome. My name is Zdeněk Hanzálek and you are watching the 71st talk of the scheduling seminar. Today I'm happy to introduce a speaker from Asia, Zhou. Before joining Hong Kong University of Science and Technology, he earned his PhD degree from MIT's Operations Research Center and Laboratory for Information and Decision Systems. This year, he was advised by Professor Patrick Gelé and Professor Jara Podimata. During his PhD, he also interned with Microsoft Research and Oracle Labs. As for hobbies, he plays basketball and he is good in piano playing. So, Zijie, it's great to have you here and the floor is yours. So please go ahead.
Okay, so thank you. Thank you for the introduction. Okay, yeah, so hello everyone. So yeah, my name is Zijie, and actually I was just graduated from MIT, so in this May, and also I was just joined HKUST in this August. Yes, I'm a very new assistant professor. Yeah, so today I'm very happy to be invited to give a talk in this global scheduling seminar. Yeah, I think I'm studying some very a new thing about scheduling and also related with the hot topic, this large language models. And so I think today I would like to give I think the topic maybe both theoretically interesting and also practically useful. And I hope that everyone will enjoy the talk. Okay, so let me start. Let's see. Okay, so first, what is a large language model? So the definition is it's large general purpose language models that can be pre-trained and then fine-tuned for specific purposes. So we know it has it has a lot of different applications. For example, a chatbot like ChatGPT, and also some like AI search engine like Microsoft Bing, and also some autocoders like this GitHub Copilot. So it's very powerful. And actually, my research focus is on the large language model inference. So what is large language model inference? It is actually to study the process how this large language model to generate this response. So for example, if we input a prompt, what color is the sky, into a large language model, for example, let's say ChatGPT. And then we observe that it is never the case that all of all of the response appear simultaneously, right? So actually what we have seen is all of these words appears one by one. So for example, the first word can be this the, right? So we see this word is the. So in this process, this is called as prefill. So prefill means that so this large language model will process all of these words in this prompt and then try to generate its first output token. So we can just understand token as a small word. And then the next step is it will actually send back this the into this large language model and along with what color is the sky to generate the next word. So this process is called as this decode. Okay, so it will do this kind of autoregressively, do this word one by one until this whole sentence is finished. Okay, so then actually what I would like to study is that, so now for example, we know for both ChatGPT or DeepSeek, it has a huge amount of demand. Maybe it will receive thousands of requests within a second. And then, so due to the limited number of GPUs, so it's impossible to process all of these arriving requests simultaneously. And then, so in this, we say these companies, like they need to decide which batch of the request to be first processed and which should be a second and dot, 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 right? So this is a very classical scheduling problem. And therefore, so my study is on this side. So we just try to study how to schedule these requests to be processed by these large language models. Okay, and because this is a global scheduling seminar, I believe everybody have a lot of background in scheduling, so I do not introduce a lot of these things. Okay, but just like one thing is that there's a very famous metric is called total completion time. So this will be the key metrics we are using to evaluate the algorithm. So in this speech. Okay. Okay, so then let me just give a more concrete example. So in this example, let's say the prompt, so the sentence we input is what is the weather like today? And then we say it has a prefill size, so this SI is a number of words in this prompt, so now it is 7. And then suppose that we say the response is it is sunny, okay? So then we say this response length, which is this OI, so output length equals to 4. Then so its process is that first it will take input, what is the weather like today? So in the first period, it will generate this output, it. Okay. So then actually in the second period, it will try to recompute all of this what is a weather like today and also this it to generate the next word. So now we see one thing is that, so if in the first period, so we compute, we say this key and value, so we also say the KVs, which we can think about as some properties of each word, so of what is a weather like today. And if we again recompute all of these key KVs for each of these words in the second period, then this is actually waste of computation. And therefore, there is a trick, it's called this like KV cache existing in real, which is to say that, so in the prefill case, so we calculate these KVs about what is a weather like today, and we store all of their KVs into this KV cache. And so the memory usage is this 7 unit. Okay, then in the second period, actually we only need to carry back these like KVs from this cache, and again we compute the KV of this new word, so it. So then we can generate the next word. And again, we will also add this computed KV of this word it into this KV cache. And therefore, in this case, the KV cache memory usage is 8 because we add one more unit of things into this KV cache. So then we'll just process these things like word by word. So we can see each time actually we only need to compute one word. And so the memory usage will increase linearly. So at 1 unit in each time period. And because this cache is, we only need this KV cache during its processing, and therefore, if all of the words has been generated, and then we can just clear all of these memories, so we do not need to store it all of the time. Okay, so this is how we do this inference for one request. And then, so actually, so for these GPUs, it can also process this request, so in some batches. Okay, so then this is our actually mathematical model. It is quite almostly very similar with what happens in real. Okay, so we just say that suppose at time t equals to 0, we have a batch of requests which is arriving. Okay, then we need to decide a batch of requests to process simultaneously. So for example, it is these 5 purple requests. And then for each of these requests, it will have its own like prefill size S1, S2 until S5, and also has its decode size. So O1, O2 until this O5. Okay, sorry, I think here's some like typos. Okay, so yeah, so for these things, actually one thing very important is that actually the decision maker, so for making the decision of scheduling, we know the value of this S1 because it is the number of words in the prompt. So we can just observe it, right? But actually we do not know what is the value of these OIs. So because this is how many number of words will be generated by this large language model. So it is unknown. Okay, but if we put them into the batches, then it will process simultaneously, so token by token, token by token, until, for example, at this time point, so the first purple request has been completed. So then due to this continuous batching strategy, so we have like incorporated in real system. So then actually, so we can immediately add a new request. For example, it's this blue one again. So in this batch, then this blue one will process simultaneously with these like purple ones. Okay, so from the whole process, actually we have a constraint, which is this memory constraint, because each of these GPUs has a limited amount of memory to store this KV cache. Okay, so we would like to guarantee that, so the total memory usage actually at every time should not exceed this given memory limit. And we can see this problem is actually quite complicated because previously we have introduced that if we just add one request, so keep processing it, so its memory usage is linearly increased. And therefore, it is to say that suppose if we can add, for example, 5 requests simultaneously at t equals to 0, so we may not be able to process them simultaneously when they like keep processing, right? Because each of them, their memory usage becomes larger and larger during this process. And therefore, the batch size in this problem is also actually dynamic. Okay, and also very hard to determine, right? And that actually adds a lot of like complexity so to this problem, and so make it a very new scheduling problem and also very theoretically challenging problem. So here's the performance metric we would like to measure is this total completion time. Okay, so we would like to and also if we would like to find out its optimal value, then we can just solve an integer programming. But actually for this LLM inference, we need to make decisions in milliseconds. And therefore, so we are not able to like compute these integer programmings, right? And so what we would like to do is to find out some approximation algorithms. And so for these approximation algorithms, we evaluate its performance by this competitive ratio, which is evaluate its worst performance. So where all of these SIs or OIs, all of the arrival or on the and number of arrivals can determine by some adversary. Okay, so this is actually the model and suggested for this large language model inference. So this actually was suggested during my intern in Microsoft Research. And so this is the first paper. So in 2025, so I collaborated with my advisors and also people in Microsoft Research. So we first suggest this model to capture all of these like KV cache memory constraint in this inference and to do some scheduling optimization. And we find actually this problem is very complicated. And since this paper, its main contribution is about the modeling thing, and therefore we do not want to spend too much time on the getting some very optimal algorithms, and therefore we add like two key assumptions in this previous literature. So we are just saying that the first assumption is all of these input size are homogeneous, which is to say that all of these SIs are the same. And the second thing is all of these output lengths are perfectly predictable, which means that at the first time, the decision maker knows all of these value of O1, O2 until On. Okay, so then under these two assumptions, we suggest some like simple algorithm called this shortest job first. So in this case, so shortest actually depend on because all of these SIs are the same, and therefore the shortest are measured on the value of OIs. So in this, under these two assumptions, actually this algorithm completely makes sense. Because if we think about all of these SIs are the same, then if we think about these OIs, if some request has a shorter this OI value, right? So then it means that it will be processed in a faster time, right? And also it will take smaller amount of memory. And also this actually improves the concurrency, right? And therefore there's no reason to delay these kind of jobs. And that's why we do this kind of shortest job first. And also our algorithm, it's actually the full name is called as the memory constraint shortest job first. Because even if we know the processing orders, there's still some challenge about, for example, how many requests to be batches for at every time period. So in our previous literature, we also find some interesting methodologies to quickly control we say the dynamic concurrency, and so that this memory constraint never violated. But so we see these two assumptions are actually quite strong and also not that realistic. And therefore, for today, I would like to introduce two of my recent works. So try to relax these two assumptions and try to make the whole problem to be more like to solve the whole problem. Okay, so for the first part, I would like to introduce the first work, which again still assume the second one. So let's assume all of these output lengths are perfectly predictable, but we completely relax the first constraint, the first assumption, which is to say all of these input size can be determined by an adversary. Okay, so this work is collaborated with a student Meishuan Wang, an undergraduate student, very excellent undergrad student. So from Tsinghua University, Department of CS, and also with Professor Yingyu Ye. Okay. So firstly, in our paper, we prove like under this model, given that like all of these input size can also be determined by an adversary. So no matter we think about minimizing the mix span or minimizing the total completion time, it is an NP-hard problem. Okay, so the main idea is to reduce to a three partition problem. Okay, so then we want to say that so for most of the like algorithms so used in real, so because in real system, so these companies actually in real system the algorithm in this part they use is first come first serve or shortest first. Okay, so try to elaborate that under this general model. So this algorithm actually does not work, or we say it has a very bad performance, and also that's why. So these industries would like us to try to help improve this algorithm, right? So here, let me just give a very quick example. Okay, so let's just think about for this shortest first algorithm. So for shortest first algorithm, we just say we prioritize requests with smaller response length OI first. Okay, so then let's see this example in the right. So now I have two types of requests arriving at t equals to 0. For the first type of request, it has this prefill size equals to m, which is a memory constraint, so square root of m minus 1. And it's like output length is just 1. Okay, and there are m number of these type 1 requests. And for type 2 request, so its prefill size is 1 and its output length is 2, and there are m to the 1.5 power of these type 2 requests. Okay, then if we use this shortest first algorithm, so it is to say that we want to prioritize the type 1 request because 1 is less than 2, right? And because we have this m amount of this type 1 request, and therefore, so we see the total completion time is we first need like the square root of m dispatches and some of their like times, right? And then plus the waiting time and then plus the processing time of the type 2 request. Okay, so we get this is the total completion time for this shortest first. And then we don't say the optimal algorithm, right? We just consider some other schedules. For example, some other schedule is we first prioritize to process all of these type 2 requests. And then we process this type 1 request. And then if we just like divided their total completion time, we can find that so the compare ratio is at least so in the order of square root of m. Okay, so because this value of m is very large, so usually in real, so its unit, so we say the KV cache unit of a GPU is usually about like a 150,000. Okay, so which is a very large number, and therefore even if you have like square root of this m, so it's a very large, it's a very large number, right? And also now we have for these GPUs, so it is like upgraded from like A100 to H100, and therefore this value of m becomes larger and larger, right? And therefore, if we think about this scheduling, it also becomes more and more important because if you have a compare ratio related to this value of m, then when this m becomes larger and larger, your performance also becomes worse and worse, right? And also, like you may also ask that, okay, so if we think about this shortest first with some other metrics, for example, if we prioritize request with a smallest value of like Si plus Oi or something like Si times Oi or Si divided by Oi, so we actually will all try this in our paper. So we find it's very, very easy to find out some counterexamples, okay, to make its compare ratio to be related to this value of m. And therefore, we can see that actually in this problem, it will be very hard to develop some algorithm with a constant compare ratio, which does not relate to this m. So this needs to, so we just say like this first come first serve or shortest first. So it's very like general algorithms, right? So if we would like to design some better algorithm, we really need to understand the structure of this LLM inference in a very deep way. Okay, so then let me just try to introduce step by step of our algorithm. Okay, we first suggest a quality metric. So this is to say that we previously due to some like we try a lot of different metrics, so we find it's actually very hard to find out one metric. So based on each single request, okay. So to say that, okay, if we compute something about this request, then we just sort this kind of request. So it's very hard to do in this way. So it's very hard to find a very good metric. And then instead, what we are doing is we define some quality metric on a batch. Okay, so this F matrix, so here this X is actually a set of requests. It actually try to evaluate we say the priority of one batch. So its value is equals to the sum of all of its decode length, so output length, OIs in this batch, and divided by the batch size squared. Okay, so this is our quality metrics. So so here like I think we can also give a quick example here. So about like try to understand this quality metrics a little bit. Okay, so in this example it's very simple. So we say if we have again we have two batch. Okay, so in the first batch we have like n1 amount of requests with prefill size s1 and output length o1. Okay, in the second batch, we have N2 request with prefill size S2 and O2, or output length O2. Okay, so then in this case, if we consider this, for example, I mean, the memory limit is exactly the same as, for example, we can just like put all of the batch one simultaneously. Okay, so if this m equals to this value, then we think about the total completion time. If we prioritize batch 1 over batch 2, it is something like O1 and 1, which is a processing time of all of these batch 1 requests, and plus this O2 and 2, which is a processing time of all of these batch 2 requests, and plus this O1 and 2, which is a waiting time for all of the requests in batch 2, right? And then conversely, if we try to prioritize batch 2 over batch 1, so total completion time becomes this O1 and 1 plus O2 and 2 plus O2 and 1. So in this very, very simple example, which is to say if we have a lot of these homogeneous requests. And then if we want to decide whether we prioritize batch 1 or batch 2, we just need to compare the value of O1 and 2 or the value of O2 and 1, which is also equivalently to say whether this O1 over N1 is less than O2 over N2. Okay, then if we think about our quality metrics, so this is exactly the same with this in this example, right? Because if we have a batch of homogeneous requests, then the sum of OI is just the batch size times OI and divided by the batch size square, which is just OI divided by the batch size. Okay, so this is how we just try to motivate this metric. But we see that in this problem, so all of these SIOIs are heterogeneous, and therefore it's actually quite hard to like summarize these kind of things, right? And then so we just like first place this quality metric here. Okay, so so the next thing is that so if we now have a quality metric on some batch, but then how to design some scheduling algorithm, right? Because we see for this problem, it's not try to decide batch by batch. Since all of these requests, they may end in different times, and when one request ends, I need to just add one more request into this batch, right? And therefore, maybe except for the first batch, then in the future, what I would like to do is to add a request one by one into different batches. Okay, so therefore it's still pretty unclear about how to design some algorithms. So then let me introduce a very interesting idea about doing this scheduling. So our idea is to say this. Suppose that we have n requests. Then let's just try to find out one batch so that this batch can achieve the smallest value of this f. And also the we say the memory usage at any time in this batch should be bounded by this m. Okay. So suppose for this batch, this is 1, 2 until this n1. Okay, then let's just get rid of all of these n1 requests. So among these n minus n1 requests, so let's again try to find out another batch so that its f score is the smallest. Okay, so for example, this is n1 plus 1, n1 plus 2, something to this n1 plus n2. Okay, we just do this sequentially and until we have a like sequence of these batches. Okay. But actually, so in real, we should not process in this way, right? Because for example, if we see in the first batch, so when request 1 has been completed, so actually we can immediately add something as request as another request, right? Follow about it. So then our algorithm is to say that the reason we would like to form this batch is actually we would like to sort these requests. So how can we sort this request? We just try to sort in the way that what is a sequence about each request is added to each of these batch. Okay, so which is to say we should always prioritize the requests in the first batch, and within this first batch, so we just try to order these requests by ascending value of their OIs. Okay, so then now we have a sorting, right? So we say this request is 1, 2 until this one is n1. So starting this one, it should be n1 plus 1, n1 plus 2 until this n1 plus n2. So now based on this methodology, we have a clear sorting of all of these requests. So then what we do in this schedule is that, so we try to process in this order, okay? And each time we try to add this request as early as possible, so given that the memory constraint will not violate it at any time. So the real schedule will be something look like the right below part. Okay, so this is actually our schedule. And so next part, we would like to claim that, so actually this algorithm has a constant compare ratio. And we here we have this so here we have, sorry, I think there is a question. Let's see. SI is not important for algorithm design. Oh, okay, no. So SI is very important because of okay, so if we think about this F score, right? So F score is the sum of OIs divided by the batch size square. So if some request, it has a very big value of this SI, then actually your batch size cannot be very large, right? So this means that, so we just try to use this batch size square to automatically like to consider these like values of SIs. Yeah, because if you have very large SI, so the memory usage will start with SI plus 1, SI plus 2. Okay, so then you cannot add a lot of things in the batch, so the concurrency will be small. Okay. Okay, so then let me just quickly introduce this constant compare ratio proof. Okay, so it's a very complicated proof, and I don't think I can explain it in a very clear way. So within just like several, maybe like 10 to 20 minutes. Okay, so just let me give some very high level ideas. And in our paper, we have a very detailed and rigorous proof here. Okay, so mainly we just want to use this like combinatorial optimization ideas. So we try to find some alternative schedules compared to our schedules, and we can bound their like total completion time, and then we find out a way to compare with like this OPT solved by this integer programming. Okay, so the first step is we try to like upper bound this like our algorithm schedule by something called this arc separate. So this is quite simple, which is just to say that previously we have this a lot of this batch, right? And then we just try to make the schedule to be like as like so try to like add each of these requests as early as possible. Okay, so now if we would like to upper bound this total completion time, let's just try to move this, for example, this kind of blue request again, go back to their batch, right? So then we try to delay all of these requests, and therefore it's clearly that this total completion time is less than this like arc separate. Okay, so the next part is very important because in our previous this methodology, so we decide this batch by batch. So we can see that a key thing is, so here we can say we want to find a batch which has the smallest this F score and also this memory constraint does not violated. So here we only have an upper bound of the memory constraint. We do not have a lower bound of the memory constraint, right? And therefore, it is also possible that maybe in some batch there's only one request. So this will definitely happen. Okay, and therefore, so the second step, so we say this out group is to say that we try to put these like put this batch together. So try to make them together. Okay, because each of them they may not use full of these memories. Okay, then let's just try to put them together. Okay, and how much batch should we put? So we should put until if we add one more batch in the current batch, then they will like violate this memory constraint at some time point. Okay, so this part is called this out group, and we also find we use like here, although it's a little bit complicated in mathematics, but actually we find out so the total completion time of arc separate can be bounded as 4 times the total completion time of this out group. Okay, so the next part is called this outline. Okay, so this is also a little bit complicated because previously we have this kind of so now for this out group we have a very huge of this batch, right? And we have a very like a different these values of SIs and OIs, so it's very hard to measure like it's always say quantify its like total completion time, right? And therefore one of our idea is just like in very high level we try to make each of the batch have the, so we consider another schedule or we think about another problem. Okay, so we again have these kind of batches, but in each batch, all of these requests have like the same length. Okay, and this same length equals to the average of the previous, we say this like heterogeneous batch. Okay, so this is something called this align, and also we can prove it is like it can be bounded by 2 times the total completion time of this out group. Okay, so then what we want to do is try to bound this opt. Okay, so for the opt which is solved by this integer programming, actually we really did a lot of numerical experiments. Okay, so we actually find for this integer programming optimal solution in this numerical experiments, so there's almostly no pattern. Okay, so it's almostly there's no clear pattern about what this optimal looks like, and therefore we can still think about so we can only think about how to bound this opt, right? So a very like high level idea is to say that we would like to introduce this something called opt transform. So it is to say that we try to delay a lot of these jobs, and so that after delay, we can again put them into like batch by batch, and in each batch, so their length is homogeneous. Okay, so we can just find a constant to bound this thing. Okay, so we find that actually we can actually use a factor of 6 and by some constructions to achieve this. And finally, we can just use this to compare with this OPT transform. So, sorry, compare with this alg line. Okay, so we can find that they have the same pattern, and also with some with some this kind of rigorous comparison, we can find this alg line is rigorously bounded by this opt transform. And so combined with all of these things, we can finally prove this total completion time of this algorithm is bounded by 48 times the total completion time of the opt, which is to say the compile ratio is bounded by 48, which is a constant. So I think this is a very amazing result. Okay, and actually, so this 48 is a very, very, very loose approximation. Okay, so I think so because for the like for the classical algorithm and heuristics, it's their compare ratio always like related to the value of m, and so now we have some constant. It will be okay, right? But this constant is really not tight. So actually, so if I try to construct some this kind of worst case, so I cannot say they are exactly the worst case. Okay, just the worst case I can find. Okay, so what I can find is the compare ratio is actually bounded by 1.5. So I cannot find any instance to make the compare ratio to be greater than 1.5. Yeah, but like this is just some conjecture. Okay, so I'm not able to prove it. Okay. Okay, so this is for the proof of this algorithm. And then there's one key thing is that, so here, so let's go back to our algorithm. So in our algorithm, so we see that we first need to try to find out this batch with the smallest value of this F score, and so that this memory constraint is bounded by this capital M. So this is also very hard to compute, right? And therefore, we also, if we want to implement it into real systems, so we also need some like approximations. So first to solve it, so if we want to exactly find the optimal this kind of F batches, so the algorithm we want to use is this dynamic programming, right? And then if we would like to approximate, so here there are like three algorithms I'm suggesting. So depending on the value of n, so which is the number of requests. So the first is this scale dynamic programming, right? So it is like 1 plus epsilon optimal. Yeah, but this still like I suggested if we only have less than 200 number of requests. So based on our numerical computations, and I think these two algorithms are actually more practical. Okay, so especially the algorithm 3. So algorithm 3 is called as local swap search, which is to initialize a batch with the ordered Si plus OI, and then we just try to iteratively swap this request, okay, to improve this F matrix. Okay, and so we just swap all of the requests and until we cannot improve this F matrix, and then we are done. Okay, so there's no local guarantee for the optimality, and the complexity is O n squared. So I think when the n is less than or equals to 500, so this will be a very practical algorithm. Okay, and when n is much larger, then there's a very very approximated algorithm. It's called this like quantile greedy. So it is to say we just sample a subset of requests and compute its quantiles for this Si plus Oi and Oi. Then we just try to, based on these quantile thresholds, and try to fill this remaining memory with requests sorted by this Oi divided by Si plus Oi. So it's a very like approximated way. Okay. Okay, so usually we will suggest this algorithm 3, and I think it will be very enough for the real use. And then let me just introduce some numerical experiments. So here actually so different with the we say the CS papers. So actually so for most of these LLM inference so people so they are studying this problem in the CS system field. So we can find that in many papers they are claiming that so this shortest first algorithm is very practical. Okay, I mean like in this like academic study. So I think there's one very key thing is that so usually when people run some numerical experiments, they only use one single data set. So we just think about in one single data set, for example, this like public conversation data set. So this is a very well-known data set in this inference field. So all of these rows, so there are some conversations, and therefore we can see, we can imagine that so the variance of we see the prefill size and decode size will not be very large, right? So because all of them are just conversations, so we can see, for example, here in the first figure, so for the prefill size, which is an input tokens count, so almostly most of them are the same. And as we have suggested, if all of these like SIs are the same, then shortest first definitely makes sense. But actually, so in real, if we want to think about this inference, we are not trying to only collect So we are not trying to only collect requests from like one type of this kind of business, right? So it may not be all of these conversations. So you can have some conversations. You can also maybe have some like this kind of, we say, archive summarization. So if we would like to think about this archive summarization, then people will usually input some archive papers. So then it's a very, very long like prefill, right? So in this case, we can see the prefill size maybe like go to like this 3,000, 4,000. Okay, but maybe it's like we say its output token may not be very long because we are just trying to actually ask it to summarize one paper. Okay, so this is another type of requests. And then we try to mix these two data set together, and we have a, like a combined data set. So this will be roughly similar to what I observed in real industries. So which is so usually speaking, so this like prefill or decode size will be will similar as some like similar as an exponential distribution, but with a small heavy tail. Okay, so this is actually, I think, the most similar distribution with the real data sets. Okay, and then we just try to compare all of these algorithms. So firstly is the blue curve, which is a first come first serve. It is a worst strategy, right? Yeah, and the second one is this like shortest first, and then so this like sorted F quantile and swap is how is our algorithm. We just try to like approximate, right? So mainly so this sorted F swap, so this red curve, so the lowest part is the performance of our algorithm. And also we suggest something like this sorted LP and LP swap. So these are some algorithms, so I did not cover today, but we have it in our paper. So there are some like more computationally intensive algorithm because it needs to solve this linear programming in many times. Okay, but we can find that actually in most of these points, so the best distorted LP algorithm actually, so this sorted LP, which is this light blue curve, is actually worse than our sorted F swap. Okay, and then if we combine these two ideas, so use this, we both solve the LP and also we use our F matrix, we can see that its performance is almostly the same as if we only use this F matrix. Okay, and then we can see that our sorted F is, if we consider both the computational like complexity and also its performance, we can see actually this will be the best algorithm compared to all of these. Okay, so it's theoretically sound and also practically very useful. Okay. So this is how we solve the first assumption. So how to try to relax this assumption. Okay. So then the second work I would like to quickly introduce is try to relax the second assumption, which is to say if we do not have the perfect output length prediction, then how can we do this scheduling? So this is collaborated with an undergrad student, Zijie from Peking University, Department of Mathematics, and also collaborated with Professor Ying Yan. So this is motivated by that in real, like actually, although we do not know this value of OIs, but we can definitely have some very simple machine learning predictions. So for example, there are two types of prediction. The first type is to use machine learning. Maybe we can think about this as a classification problem. We can use the previous training data set and then add each of the requests before they are processing. We just predict how many output token will it generate it, right? So we put it to be short, medium, or long, different categories. Okay. And also there's another kind of prediction is from the user's perspective is to say, for example, this Claude, it will let users to input the value of min or max tokens in output when calling its APIs. So this is actually try to get some predictions, right? Because the user first need to type in these parameters, then so it will call this API, right? So actually you know what is the minimum number of tokens and the maximum number of tokens. So there are some different types of predictions. Okay. So then we just build a model. So most of the things are the same with the previous model. So the only different thing is that now we think about this OI it belongs to some interval, so from L to U. So here, let me just first suggest a warm-up model. Okay, so in this warm-up model, so all of these OIs are belongs to the same interval. So let's say, for example, I have 1,000 of requests, and now the only information I have is, for example, they're all conversations. So therefore, their output length may be between 500 to 1,000. Okay, so this is our information. And then we define this alpha equals to L divided by U. And by the way, so in this work, we have to assume like if we want to get some zero results, we have to assume all of these prefill size is the same. Okay, and I will also quickly introduce if they are different, then how can we do? Okay. Okay, so in this model, again, all of the constraints are the same. And one thing different is that because now we do not know the exact value of these OIs, and therefore we cannot, so no schedules, except you make the things to be very conservative, right? So for most of the schedules, you cannot guarantee that the memory does not violate it because you do not know what is the value of this OI, right? And therefore, we are saying that if there are some memory overflow risk, so we can allow some job cancellation. So for example, if we try to add 5 requests in the same batch, and during this process, we find, okay, maybe only we can add 4 in the batch, right? And the 5th one, if we still process it, so it will try to violate the memory constraint. Okay, and then what we want to do is to cancel this job. So by cancel, it is to say that we just put it back into this queue and we just ignore all of its existing, or we say its generated output. So in the next time, it needs to process starting from the first token. Okay, so this is what we call as this job cancellation. Okay, so evaluation metric is again this total completion time. Okay, so then for the hindsight benchmark, so this is what we just like we need to have a benchmark, right? So now the hindsight benchmark is we just assume all of these OI are known in advance. And because in this paper, we again assume all of these prefill sites are the same, and then the hindsight benchmark is just the shortest first, okay, based on all of these known OIs. So it's something we cannot achieve, but can be seen as an benchmark. Okay, so we also measure the compare ratio over this hindsight optimal. Okay, so then we want to introduce some scheduling algorithms. The first one is a very naive benchmark algorithm. We call it as Amax. So because let's think about the problem now. So now we have all of these S are the same, right? And also we know for all of these requests, we only have a prediction interval about their output length is between L and U. Okay, so then actually at time t equals to 0, all of the requests to us, they are almostly identical. Okay, and then naive benchmark algorithm is just to say that let's treat all of these OIs equals to U because we do not want to have any memory overflow. But then what is a big issue? The big issue is that the concurrency may be very bad. Right, because for example, suppose most of these output length equals to 500, but you think about there are 1000. Okay, so then we can just think about maybe we can actually put maybe 10 requests to process simultaneously, but now we only put 5 of them process simultaneously. Okay, so this hurts the concurrency. But how to evaluate its compare ratio is also a very hard mathematical proof. Yeah, so it's quite interesting. So we need something called a memory preserving proof technique. So this is come up with the undergrad student. So I think it's a very smart idea. Okay, so finally, I will skip the proof, and if you are interested, you can check our paper. So but finally, we find out its compare ratio is bounded by, so roughly speaking, so this alpha, which is L divided by U. So it's negative 1.5 power to its negative 2 power. Okay, so bounded in this interval. So next we're thinking about, can we get something much better? So then the key algorithm we want to introduce is called this Amin. So for this Amin, it actually uses a completely opposite idea, which is to say that at time t equals to 0, let's treat all of these requests as their OI equals to L. So equals to a lower bound. And then let's just try to process. So in this way, so the concurrency should be the maximum, right? And maybe it will be larger than hindsight. And therefore, so what is the shortage? The shortage is we may have to delete some or cancel some job at some times. Or maybe we need to cancel a lot of jobs, right? But like one thing is that we can add some like learning ideas here. So for example, if a request have been processed for 200 tokens and then it has to be canceled. So then what is the information we have? The information is that, so it will have at least 200 tokens. Okay, so with this information, then we'll update this 200 to its new lower bound. Okay, so then this is to say that although we may need to, so at the beginning we are too we are overly optimistic, right? Make the concurrency to be too large. But during this process, we can try to use this kind of learning ideas and try to make the extent of our optimistic to be smaller and smaller, right? Because we have the more and more accurate information of this lower bound. Okay, so this is the key idea behind this algorithm aiming. And then here we can prove two things. First is it is asymptotically optimal. And the second is that this expression is its compare ratio, so it equals to some Rayleigh quotient. And also we can there's a proposition we also rigorously prove that so for this Rayleigh quotient it actually is uniformly bounded by the log of alpha negative 1. And therefore, this is a very exciting result, right, compared to the Amax, because the compare ratio of Amax is from 1.5 power to the like quadratic thing, and now we improve it to a logarithm. Okay, so this is a very interesting and impressive theoretical improvement. And also then, so two things. So one is how to extend it to this kind of more realistic disjoint interval prediction. So this is very simple. So now, because compared to the previous we say L to U, now we have more informations, right? We have L1 to U1, L2 to U2, so we have these kind of different joint prediction intervals. Then we just take, for example, we first make a prediction, right? For some request, if it belongs to L2 and U2, then we just first think about its lower bound equals to this L2. Again, so when it's during this inference process, if it is cancelled, let's update its lower bound. Okay, so we just use exactly the same idea, but with initially different lower bounds. So we can definitely also show that the algorithm in this case is also in the logarithm order. Okay, and also another thing is that you may ask, okay, so in the first paper we try to have the assumption 2 and relax assumption 1, and now we try to just make the assumption 1 and relax assumption 2, but like can we just try to both relax these two assumptions? So the answer is definitely yes. But maybe we cannot get some very theoretical sound results. Okay, so the idea is that we can think about this Amin algorithm. So if I see this as an algorithm, or we can think about it as some like algorithm structure, right? So which is to say that it can be definitely so combined with some other algorithms. So for example, think about the previous, we say this F-score algorithm. So we can again just like take all of these OIs at the lower bound and input into the previous sorted F algorithm, right? And then if we if like the memory constraint if the memory overflows at some time point, again let's just update these OIs and again use the previous this kind of F matrix to make the decision, right? So you can see that this is actually a not very like restrictive algorithm. It can become some structure. Okay, so this is also tested in the numerical experiments. So we can see that, so we try to use some like rough prediction. So we say the prediction is between 1 and 1000. So we can see this Amin algorithm, this blue curve is very close to this benchmark algorithm. And if we have more informations, then actually they are very, very, very close, right, between this Amin and benchmark. So we can see in this way, so Amin is almost as good as the benchmark algorithm. So which is a hindsight, so something we cannot achieve. Okay, and we also consider some other overlapping interval predictions. So we can also see all of these Amins have very great performance. And therefore, I think this will become a very like practical and interesting algorithms ideas to solve these type of questions. Okay, so I think yeah, I spent like 48 minutes, so within the time constraint. Okay, so this is all I would like to cover, and I hope that I introduced a new question like to the scheduling community, and also I think if you are interested in this problem, so feel free to reach out to me, and maybe we can discuss more and even have some like collaborations. Yeah, I think this is some like very theoretically interesting problem and also practically useful. So I'm looking forward to see more and more people joining these problems and solve this, try to make this large language model inference to work better and better. So thank you very much. And this is my contact email. Thank you.
Okay, thank you. And now the questions. Is there any question? So I think you should be able to unmute. Allow participant to unmute, right? So you can either write it in the chat or you can unmute and ask. So if not, just let me wrap up. So you have like kind of online algorithm which progressively treats the requests in practice, right? But here it was solved as offline problem, or you knew all the requests in advance, right?
Yes, yes, yes. Yeah. So here, like, this is also one of the assumptions to say that we need to have all of these requests arriving at t equals to 0. And now like I'm also collaborated with Professor Ying Yu about like how to make this to be fully online. And we also have some like great results and maybe we'll publish soon. Yeah.
Okay, good. And if you have tested it in practice with those Microsoft Research Labs, or at least in some simulation of their typical requests, or do you have a benchmark of typical requests for MML?
Yeah, so this is also one thing I would like to suggest is that so for this large language model inference, if we would like to do these we say some numerical experiments, so there are mainly two ways. So the first way is that if we really have GPUs, so then we can use this engine. So this is public engine called VLLM. So VLM. So it's a public engine designed by UC Berkeley Skylab. And also now it's a very huge community. So almost all of the academia people and the industry people, they are using this engine to like serve this like large language model inference. But the prerequisite is you need to have some GPUs. Okay. And the second thing is that if you do not have the GPUs, so we can still do this research. So which is there's some like public simulator called video, VIDUR. Okay, we can also find it on GitHub. So we can also download it and run it on our CPUs. So and then we can just try to revise its schedulers. So now its current and default scheduler is just first come first serve. Then we can just revise it into anything else. And then you can see all of my experiments are run by these public simulators. Yeah, so these simulators, actually, I think there's a paper to say its accuracy is more than like 90%. So it's just so its idea is very simple. So try to collect a huge amount of data sets. And just like for each of these traits, I think it has some like different models, like linear regression, some random forest to capture what is the batch processing time, and so these kind of things. And then like it builds this simulator and then make it to be public and everybody can use. Yeah. So this is how we run these experiments. Yeah.
Okay, so you approximate the processing time from the previous requests, and you use, for example, linear regression to see what's the typical processing time depending on some other parameter, right?
Yes, 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 yeah, yeah. So this is how the simulator did it. Yeah, yeah. So they are developed by the company. Yeah.
Okay, thank you.
Mhm.
So, any question anybody wants to ask? If not, so let me thank you, Jie, once more, and thank you for a very informative talk. We
No,
don't
thank
have
you.
these applications often, and it's good that it's coming. And let me just mention the next talk in our seminar. It will be given by Rachel Shen, and she will speak about outpatient appointment scheduling with waiting time limits. So she will speak in 2 weeks from now, 12th of November. And the seminar will start at usual time, so I hope to meet you, and I wish you productive 2 weeks, and hope to meet you again in 2 weeks. Okay, thank you very much. Bye bye.
Thank you, Jerry. Thank you.
Yeah. Thank
Bye
you.
bye.
Bye-bye. Yeah,
Bye
bye-bye.
bye.
Bye bye.